Usually when you lose something, say your car keys, you know exactly what you're looking for.
Oh, yeah, you have a completely clear mental image of them.
Exactly. It's like this little jagged silver piece of metal, maybe attached to a black plastic fob. It's a really clean, straightforward search. You know the parameters.
Right, you're not going to accidentally mistake a banana or like a coffee mug for your car keys?
No, definitely not. But imagine trying to search a massive pitch black room for those keys, except you don't actually know what keys look like.
That sounds incredibly frustrating.
It is. You don't know if they're made of metal or plastic, or if they're heavy, or you know if they even make a jingling sound at all. You're just blindly groping around in the dark, hoping you bump into something that feels like it might just, well, unlock a door.
Which honestly perfectly mirrors the kind of diagnostic muddy waters of what we're diving into today.
It really does. So, welcome to the Deep Dive. Today, we are taking you on a journey to answer a question that, for a long time, used to belong entirely in a late-night philosophy dorm room.
The ultimate "what do you reckon" question.
Exactly. But it has quietly transitioned into one of the most rigorous experimental sciences of our time. We are exploring the search for extraterrestrial life.
We're finally asking, is there anything else alive out there?
And more importantly, how do we actually find out? Because over the last 30 years or so, we've seen this monumental shift, haven't we?
Oh, absolutely. It's gone from pure speculation to massive research programs. I mean, we're talking billion-dollar space agency budgets, dedicated orbital missions, and highly specific testable predictions.
We are getting right into the actual mechanics of it. And if you're listening to this and worrying that you haven't taken a biology or astronomy class since, like, high school, do not stress at all.
Not at all.
We are going to be your guides through the source material today, and we'll unpack every single technical concept as we go. So no prior science background is needed.
Just bring your curiosity.
Right. But to even begin this search, we run into that missing keys problem right out of the gate. Before we can look for life, we have to actually define what we're looking for.
And it sounds like a mere technicality, right? Like, obviously we know what life is, but it's actually the foundational problem of the entire field.
Because it's surprisingly difficult to pin down.
It really is. Every time we try to write a strict, comprehensive definition of life, we end up either excluding something we intuitively know is alive, or we accidentally include something we definitely know is not.
NASA actually has a working definition for this, right?
They do.
Yeah.
They define life as a self-sustaining chemical system capable of Darwinian evolution.
Okay, so meaning it can survive on its own, it can reproduce, and it adapts to its environment over generations.
Exactly. It sounds very official and airtight.
But the source material describes this definition as highly leaky.
Very leaky. Let's just test it out. Think about a standard campfire.
Okay, a campfire.
A fire consumes fuel, it grows, it uses oxygen to metabolize, and in a very real sense, it reproduces as it spreads, right? From a single spark to an entire forest.
Oh, well. Yeah, I guess it does.
But nobody looks at a campfire and categorizes it as a living organism.
Right, obviously not. And then, on the flip side, you have something like a virus.
Yes, the classic wild card.
Because we all know viruses replicate, and they definitely undergo Darwinian evolution. I mean, they mutate over time. We've all seen that happen.
We certainly have. But a virus can't actually do anything on its own.
It's essentially just a rogue package of genetic code, right?
Exactly. It has to hijack a living host's cellular machinery to reproduce. So biologists still aggressively argue about which side of the line viruses sit on. Are they alive or just complex chemistry?
The source also brings up crystals, which I thought was fascinating.
Oh, quartz crystals are a great example. A crystal grows over time, and it self-organizes into incredibly complex, highly ordered geometric patterns.
Much like biological structures do.
Right. Yet a quartz crystal isn't alive. So we simply do not have an airtight definition.
And this is a huge practical issue. If we're building a billion-dollar probe to detect life, we have to program it to look for something specific.
You have to tell the sensors what to measure.
And because the only example of life we have is us, the biosphere here on Earth, every detector we build carries a profound bias.
The carbon-water bias?
Exactly. We are programming these machines to look for carbon-based, water-dependent life.
But, I mean, I have to push back a bit here. Isn't looking for carbon in water just a parochial preference?
It's a very common and very fair skepticism.
Because just because we are made of carbon and water doesn't necessarily mean alien life is, right? We could theoretically fly right past some bizarre exotic organism because we were too obsessed with our own chemistry.
You're not wrong to wonder that.
Yeah.
But scientists defend the focus on carbon and water using straightforward chemistry. It isn't just local Earth bias.
Okay, walk me through it. Why carbon? Well, carbon is incredibly unique among the elements because it easily forms 4 stable bonds with other atoms.
Or stable bonds.
Right, and that ability allows it to link up into long, complex chains and intricate rings far more readily than almost anything else on the periodic table.
Which you need to build complex things.
Exactly. If you want to build the highly complex, massive molecules required to encode the instructions for life, like DNA or folded proteins, you absolutely need those stable structural chains.
But science fiction always loves to bring up silicon as the alternative. Like you always see the silicon-based rock monsters in movies.
Oh, the classic rock monster, yes. And looking at the periodic table, silicon actually sits right below carbon, and it also forms 4 bonds.
So why not silicon aliens?
The geometry is similar, sure, but the bond strength is the critical difference here. Silicon's bonds are significantly weaker than carbon's.
Oh, I see.
So those complex chains just fall apart much easier in the chaotic, hot environment of an early planet. It's too fragile for complex biology. Furthermore, consider respiration. When a carbon-based organism processes energy, like you or me, it exhales the waste product as carbon dioxide.
Right.
And carbon dioxide is a gas. It floats away easily.
Okay, yeah.
If a silicon-based organism were to process energy and quote-unquote exhale, its equivalent of carbon dioxide is solid silica.
Wait, solid, meaning it would essentially be exhaling solid sand.
Yes, exactly.
Oh, wow. That sounds exciting.
Incredibly awkward, yes. It would make biological waste disposal vastly inefficient from an evolutionary engineering standpoint. You just fill up with sand.
So carbon is structurally superior for building complex biology, period.
It is. It really is the best Lego brick available.
And then we have water. Water isn't just common across the universe. The source points out it possesses a set of chemical properties that are practically magical for fostering biology.
Magic is a good word for it. It's a tremendous solvent, meaning it dissolves more substances than almost any other liquid.
Which allows vital chemicals, minerals, and nutrients to circulate freely, like in our blood.
Exactly. It also remains in a liquid state across a very forgiving wide temperature range. But honestly, the strangest quirk of water is what happens when it gets cold.
It expands when it freezes.
Yes. And that quirk is arguably responsible for life as we know it. Solid ice is less dense than liquid water. That is why ice cubes float in your glass.
Right. But why is that so crucial for life?
Well, imagine if water behaved like nearly every other liquid in the universe and became denser as it transitioned into a solid state. Ice would sink.
Oh. It's strange to think about the physical mechanics of that. If ice sank, oceans and lakes during a harsh winter would freeze solid from the bottom up.
Exactly.
The deepest parts of the ocean would just terminally fill with dense ice, eventually locking up all the water and basically killing everything inside.
But because ice floats, it forms a protective, insulating layer on the surface of a body of water.
It shields the liquid ocean beneath it from the freezing air.
Right, keeping the environment safe and warm enough for marine life to survive the winter. So, water and carbon really do look like the absolute best chemical building blocks available, regardless of what planet you're on.
Okay, so knowing that, where do we actually look?
Well, for a very long time, scientists adhered to a strict rule called the habitable zone, or you might have heard it called the Goldilocks zone.
Right, the orbital band around a star where a planet is not too hot and not too cold, but at the exact right distance for liquid water to pool on its surface, warmed by starlight.
That was the golden rule.
But that assumption was completely shattered in 1977. And the wild part is, it didn't happen by looking through a telescope. It happened deep underwater here on Earth.
The Galapagos Rift discovery, it completely tossed out the rulebook.
The scene described in the source is just incredible. You have this submersible descending thousands of meters down to the absolute bottom of the seafloor.
Total, crushing darkness.
The ambient water temperature is near freezing. Zero sunlight can penetrate that deep. And the prevailing scientific dogma of the time dictated that this should be a barren, dead wasteland.
Because all food webs ultimately relied on plants harnessing sunlight through photosynthesis.
Right. No sun, no plants, no life.
That was the biological law until they turned on the lights.
Yeah, the submersible turns on its floodlights, and they find hydrothermal vents.
Which are these massive fissures in the ocean floor where superheated, toxic, mineral-rich water is violently spewing out of the Earth's crust into the freezing dark.
And instead of a dead zone, the area around these vents is teeming with dense ecosystems. They found tube worms the length of a person, weird pale crabs, giant clams.
You can just imagine the shock of the biologists looking out that porthole. They are staring at a thriving metropolis operating in a pitch-black, unplugged freezer.
That analogy is so perfect, it's an unplugged freezer. But wait, if there's no sunlight penetrating miles deep into the ocean, these organisms can't be using photosynthesis?
No, they can't.
So they must be fueling themselves directly from the toxic chemicals pouring out of those vents.
They are. The phenomenon is called chemosynthesis.
Chemosynthesis.
The bacteria down there have actually evolved to extract energy from harsh chemicals, specifically hydrogen sulfide rather than sunlight.
Oh, wow.
They consume the chemicals, and in turn, the giant tube worms and crabs consume the bacteria. The entire ecosystem is completely decoupled from the sun. It runs purely on the internal heat and chemistry of the Earth itself.
And these organisms fall into a broader biological category known as extremophiles, right?
Yes, extremophiles are organisms that survive and even thrive in conditions that would instantly destroy standard biology.
And the source notes that since that discovery in 1977, biologists have found extremophiles everywhere we previously assumed life was impossible.
Absolutely everywhere. We have found them living in water heated to 120 degrees Celsius.
Wait, that's well above boiling.
It is. It's kept liquid only by the extreme deep-sea pressure.
That's wild. They've also been found in highly acidic environments with a pH near 0. And it's super salty, salt-saturated brines.
We've even found them miles underground, living inside the microscopic pore spaces of solid rocks.
Solid rock.
Yes. And they metabolize at such an unbelievably slow rate down there that a single cellular division might take an entire century.
A century just to divide once. That is wild. The source also mentions organisms frozen in Antarctic ice for thousands of years that can simply be thawed out and revived.
Which is mind-blowing.
And then there's the bacterium called Deinococcus radiodurans.
Ah, yes. One of the toughest organisms on Earth.
It can survive radiation doses thousands of times higher than what would be lethal for a human. And it manages this by, I had to read this twice, literally allowing its own genome to get shattered into pieces by the radiation.
Right, the radiation obliterates its DNA.
But then its cellular machinery just neatly reassembles the fragments back together like a puzzle.
It is a phenomenal mechanism.
It really is.
And the broader implication of extremophiles is that the habitable zone, that narrow, starlight-dependent band around a star, was really just a preliminary guess. Life's operating manual is incredibly thick.
It can tolerate a vast range of conditions.
And crucially, it does not strictly need surface starlight to endure.
So if starlight isn't a requirement, that fundamentally reshapes where we should be looking in our own solar system.
It changes everything.
Historically, we've been intensely focused on Mars, right? Looking for ancient, dried-up riverbeds. But if an ecosystem can survive in the dark, the most promising candidates are suddenly much further out in the cold.
We start looking at the ocean moons orbiting our gas giants.
Right, and Jupiter's moon, Europa, is a prime example of this.
Europa is fascinating.
It's slightly smaller than our own moon. And looking at the surface, it appears to be nothing more than a smooth, heavily fractured shell of solid water ice.
But planetary scientists are incredibly confident that beneath that miles-thick ice shell lies a global ocean of liquid, salty water.
And the scale is just difficult to wrap your head around. We are talking about a subterranean dark ocean, holding roughly twice as much liquid water as all the oceans on Earth combined.
It's just massive, and the evidence for this ocean is quite robust.
How do we know it's there if it's under miles of ice?
Well, the way the surface ice is fractured, shifted, and refrozen strongly indicates it's floating on a fluid layer. But more importantly, Europa interacts with Jupiter's massive magnetic field.
Okay.
The data from those magnetic interactions perfectly matches what we would expect if there were a global conducting layer beneath the ice. And a massive churning ocean of salty water is an excellent conductor.
That makes sense. But the logical concern here is the distance. Yeah. Right. Europa is way out by Jupiter, extremely far from the sun. Without solar heat, an underground ocean should just freeze solid over time.
You would think so, yes.
But there is a physical mechanism keeping it warm called tidal heating. To borrow an analogy from the source material, Europa does not orbit Jupiter in a perfect circle. Its orbit is an ellipse, an oval. So at certain points in its orbit, it's physically closer to Jupiter, and at other points it is further away. Jupiter's gravity is immense. As Europa completes its orbit, that gravity physically stretches and squeezes the entire moon.
It's a continuous gravitational massage.
Exactly. And the analogy the source uses is great. If you take a metal paperclip and you repeatedly bend it back and forth, the metal in the crease gets physically hot from the internal friction.
Right, you can burn your finger on it.
That is exactly what Jupiter's gravity is doing to the rocky core of Europa. It is bending the moon, generating massive internal friction, which produces enough heat to melt the ice from the inside out and maintain a liquid ocean.
And that tidal heating proves that a world can sustain a liquid water environment for billions of years with absolutely zero reliance on the warmth of its host star.
So Jupiter is squishing Europa. What about Saturn?
Well, Saturn has a moon called Enceladus, which is doing something similar, but even more accessible.
Accessible how?
Well, Enceladus is tiny, only about 500 kilometers across. But the Cassini spacecraft observes something spectacular at its south pole. Gigantic plumes of water vapor and ice violently erupting out of cracks in the surface, spraying directly into space.
Wow.
And Cassini actually flew its instruments right through these geysers to taste the chemical makeup.
So it didn't even have to land or drill, it just got the spray.
Exactly. And the data returned from those plumes fundamentally altered the search for life.
What did they find?
Cassini found salt water, indicating the underground ocean is in direct contact with a rocky seafloor. It also found silica nanoparticles.
What do silica nanoparticles tell us?
On Earth, they only form when super hot water interacts with rock, which is a really strong indicator of active hydrothermal vents, much like the ones at the bottom of our own oceans.
The unplugged freezers.
Exactly. Furthermore, Cassini detected molecular hydrogen in the plumes.
And molecular hydrogen is the exact chemical energy source those deep-sea bacteria use for chemosynthesis.
Bingo! So Enceladus has the liquid water, the internal sheet, the complex chemistry, and the biological fuel.
Plus, like you said, it's literally spraying its ocean out into space, offering us a free sample.
It is the most accessible alien ocean we could hope to study.
We also have to mention another moon of Saturn, Titan, because Titan is just a bizarre wild card.
Titan is truly weird.
It's the only moon in our solar system with a thick, dense atmosphere, mostly nitrogen. It has actual weather systems, it rains, it has flowing rivers, and enormous lakes.
But because it is so incredibly cold, those lakes aren't made of water.
Right. They're filled with liquid methane and ethane.
It is a landscape where liquid natural gas carves canyons into hills made of water ice. It's surreal.
If life managed to evolve in liquid methane, it would have to utilize a biochemistry fundamentally unlike anything we have ever seen.
It's a massive long shot, honestly, but discovering life there would prove that biology can arise using a completely different set of chemical rules.
So we have these highly compelling targets right here in our own solar system, close enough to send physical probes. But what about the broader universe?
That's where things get really expansive.
Because astronomers have confirmed the existence of thousands of exoplanets, right? Planets orbiting other stars.
Yes. And we now know that rocky planets like Earth are incredibly common.
But we can't send a probe to a star system 40 light years away. It would take tens of thousands of years.
No, we have to study them from a distance using light.
And this is where instruments like the James Webb Space Telescope come in. We analyze exoplanets using a technique called transit spectroscopy.
That's the one. Imagine you are observing a distant star. When a planet orbits in front of that star, from our perspective, it causes a tiny dip in the star's brightness. That is a transit.
Right.
During that transit, a minuscule fraction of the starlight passes directly through the planet's atmosphere before continuing its long journey across space to our telescope mirrors.
And as that light filters through the alien atmosphere, the different gases present, like water vapor or methane or carbon dioxide, absorb very specific wavelengths of light.
Yes, by the time that light reaches us, it has specific chunks missing from its spectrum. It carries a chemical fingerprint.
So we can decode that light and read the atmospheric composition of a planet trillions of miles away. That is amazing.
It is. And we are looking for what scientists call biosignatures.
Okay, but let me play the skeptic for a second. Looking at the chemistry, if a telescope detects oxygen in the atmosphere of a distant rock, how do we know it's aliens?
You mean rather than just a weird rock or a glitch?
Yeah. Couldn't a geological process or a chemical reaction on a dead world potentially release oxygen.
Absolutely. Which is why we aren't just looking for a single gas. We're looking for something called chemical disequilibrium.
Chemical disequilibrium. What does that mean?
Take Earth's atmosphere as the prime example. It contains roughly 21% oxygen. From a strictly chemical standpoint, that is highly anomalous,
Really?
because oxygen is a very reactive element. Left alone, it wants to bind to rocks, like iron turning into rust, or react with other atmospheric gases. It should rapidly deplete.
Oh, I see. If the Earth was dead, the oxygen would have vanished billions of years ago?
Exactly. It only remains at 21% because our planet has a vast, interconnected biosphere of plants, algae, and bacteria constantly pumping fresh oxygen into the air.
Right.
But alongside that oxygen, our atmosphere also contains methane. Oxygen and methane react destructively with each other. They should not coexist in large quantities over long periods of time.
They would just cancel each other out.
Right. If an alien astronomer pointed a telescope at Earth, they would observe this chemical disequilibrium. They would see two gases that shouldn't be there together.
And they would logically conclude that something highly active is continuously replenishing them.
Yes. That persistent imbalance is the biosignature. It's detecting a planetary chemical state that is exceedingly difficult to explain without a biological engine running in the background.
But the source material is careful to note that abiotic non-biological processes can sometimes mimic these signals.
There are false positives, unfortunately. For instance, strong ultraviolet radiation from a host star can strike a lifeless planet's water vapor, split the H2O molecules, cause the lighter hydrogen gas to escape into space, and leave a massive accumulation
Of oxygen, just sitting there.
Exactly, no biology required at all. So the scientific community demands an extraordinarily high burden of proof, rigorously trying to rule out every possible dead rock scenario before even whispering the word biology.
False alarms and scientific caution are signs of a healthy field, not a weakness.
Precisely.
So if extremophiles prove that life is incredibly resilient and telescopes prove that habitable rocky worlds and ocean moons are everywhere, the math just doesn't seem to add up.
You're hitting on the big question now.
Right. Why is the sky so quiet? This brings us to SETI, the search for extraterrestrial intelligence. They aren't looking for atmospheric gases or microbial life. They are using radio telescopes to listen for deliberate technological signals from advanced civilizations.
And they've been scanning the sky since 1960.
Over 60 years. And they have found absolutely nothing.
The silence is deafening. And it forms the core of what is known as the Fermi paradox.
UV paradox.
The paradox is the immense tension between two opposing facts. The raw ingredients and environments for life appear to be incredibly common across the universe, yet we see zero evidence of anyone else out there.
Are we just entirely alone, or are we looking in the wrong way?
Well, we have to provide the proper scale to that silence. Well, SETI has been listening for decades. The physical volume of the galaxy, multiplied by the vast spectrum of possible radio frequencies, over a minuscule blip of cosmic time, it represents a vanishingly small fraction of the total search space.
Okay, put that in perspective for me.
If the universe is a massive dark ocean, we have essentially dipped a coffee mug into the surface waves and concluded that fish do not exist.
Oh, wow. That's a great way to put it. So the absence of a detected signal so far doesn't actually rule out very much at all.
Not yet.
So, summarizing the current state of this deep dive, as of today, we have zero definitive proof of life beyond Earth.
Nothing confirmed.
Not a single microbe verified on Mars. Not a single confirmed radio transmission from the void. But the scientific baseline has completely shifted over the last few decades, hasn't it?
It has fundamentally changed. We used to think life was incredibly fragile, requiring perfect sunlit conditions. Now we know the ingredients are everywhere.
Moons are hiding vast oceans, extremophiles are surviving intense radiation and darkness, and telescopes are peering into the atmospheres of billions of potential worlds.
The field is moving from educated guesses to empirical observation. We have dedicated probes preparing to study Europa's ice shell, and next-generation observatories reading exoplanet light right now.
The question is finally becoming answerable. And the stakes of those answers are just staggering to think about.
They really are.
Because if we find life a second time, independently, just in our own little solar system, say a microbe swimming in the plumes of Enceladus, then the statistics dictate that life is almost certainly common everywhere.
It would mean we live in an incredibly crowded biological cosmos.
But if we search thoroughly, scanning the ocean moons and reading the exoplanet atmospheres, and we listen to the radio spectrum for another century, and we find absolutely nothing.
That tells us something equally profound about our place in the universe.
It really does. If the ultimate conclusion of this massive, multi-generational search is silence, if we truly are a rare, lonely, statistical anomaly in a vast, cold, dead universe, it leaves you with an overwhelming thought.
What's that?
If we were the only spark of biological consciousness out there, the responsibility we bear to protect this one, solitary, fragile biosphere we call Earth, is almost too massive to comprehend.
That is actually a really profound way to look at it. We aren't just protecting ourselves, we'd be the sole custodians of life itself.
Exactly. We're no longer just standing in the dark room blindly groping for keys. We finally know what to look for, and the search has officially begun. Thanks for joining us on this deep dive. We'll catch you next time.